Welcome to Complexity Made Simple. My name is Paul Allen, and before we get into today's video, well, I'm just going to remind you the 3 books that are on sale. Drink tea and read the paper. If you're a green belt and a black belt and you want simple instruction on how to apply your skill, design of experiments for 21st century engineers, and finally, a statistical process control for small batch production. They are all available from lulu.com and the links are in the video below. Okay, welcome to the latest video. And the subject of today's video newsletter, well, we're going to take a look at, I like to give you practical, simple explanations of things. I'm guessing that if you've ever done a T-test, a hypothesis test, probably if you've been taught hypothesis testing, it's confused the hell out of you. But I'm going to give you a practical way of doing a T-test to see if there's been a shift in the mean. And this is going to be called the end count test. I was talking to a colleague, so Leon, if you're watching, I was talking to a colleague and I mentioned the end count test to him and he said, never heard of it. Oh, I can't believe I've not made a video about the end count test. I better make one. So let's talk about what a hypothesis test is, and then we can talk about the end count test. It's very straightforward. You're doing a trial on a process. Maybe you're changing the temperature. So you're going to do the temperature at 40 degrees. You're going to do the temperature at 60 degrees because you think it might move the average performance of something that you're interested in. So this could be a dimension or a strength or whatever it happens to be. And so you're doing a test. You do some trials at 40, you do some trials at 60, and then you're doing usually you do a T-test. So normally, the test that you do for a shifted mean is something called a T-test. And out of the T-test comes a p-value. And if the p-value is low, you definitely had an effect with your new temperature. You've shifted the mean of the process, right? So that's normally what happens, and it's quite mathematical, and people get confused about what a p-value is and all kinds of stuff. Okay, but what we want to know is, when we do 2 tests, did you create the shift? Or was it just 2 groups? Were you being lucky? And 2 groups of results, which are always going to be slightly different. Did you create that with your change in the temperature? And that's what a test does. That's what a T-test does. And it normally tells you by the p-value. But I said to Leon, well, you can do an end count test. He said, what's one of those? Well, this is a test that was invented by a guy called John Tukey, I believe in the 1950s. And so this is before we had computers. So of course, the mathematics, which today is the press of a button, you had to spend an hour doing the calculations in the good old days. So Tukey wanted quick ways of doing it. And one of his quick tests was known as the end count test. And it goes like this. It's very simple. You just take the data from the red distribution and you just mark it on the scale. Okay, so I don't know how many data points you might know. Let's say it looks like that. Then on the same scale, you take the data from the black distribution and you mark it on the scale. Let's say it looks like that. Then we do what's known as an end count, and it goes like this. I count the black data free of any red interference. So I'm going to get 1, 2, 3, 4, then a red one appears in there, I will stop the count. So there's 4 this end. Then I count the red ones free of any black interference. 1, 2, 3, 4, 5. I'm gonna cut that one off there. So there's 1, 2, 3, 4. There's 5 this end. So I have 5 red data points before I hit the first black one. I have 4 black data points before I hit the red one. If I add those two together, the end count is 9. Now then, the end count, we're going to look that up on a table. The table looks like this, look. So a p-value, if you were looking for significance at 0.05, that would be a significant shift. That comes with an end count of just 7 data points. Now we're a couple of lines further down there, so we're more than just significant. We're very significant on this list because we've got an end count of 9. In other words, we are absolutely certain that our shift in results was because we played with the temperature. And that's the end count. Now it's a very practical thing that you could do. You could do this on a machine. So if you were stood at a machine without your laptop, without all the maths to do a t-test, and you were just thinking, oh, I wonder if I made this change, I wonder if the surface finish would get better. Well, you could take the surface finish of 30 data points before, maybe the red, then you decide to change the speed, or you put a new cutting tip in there or something, some simple change that you're going to make. You measure the surface finish, 20 or 30, after you've done it. You just get a piece of paper, you mark all that data on a piece of paper, and if you get an end count above 7, 7 is your lucky number because that indicates a significant shift in the process. Now I've looked this up on the internet, and the end count test is highly reliable. It will always agree with the mathematical test. So if you decide that you have a p-value of 0.05, you've got an end count of 7, when you calculate the p-value for real, it'll be around about 0.05. You'll have a significant shift. If you get the higher end counts and you think you've got a smaller p-value than that, when you do the maths, the p-value will agree with the end count. Literally the end count and the mathematics are always correct with one another. So this is a fantastic test to do. It's highly practical. You don't need any flipping maths to do it. You can do it in 20 seconds and it works. So Leon, that's the end count test. Instead of doing a t-test, I like to give you simple solutions. That's my simple solution to the t-test.